Okay, so let's start with the black body radiation. Now, first of all, what's the black body? So let's just imagine, not necessarily a black body, some objects, well, two objects, two different materials, at some temperature, at the same temperature, and there's the electromagnetic radiation in between. And let's just assume that, so this is material 1 and material 2. If you want, you can just imagine a closed container. And so, well, there's this electromagnetic radiation in between, so it's basically electromagnetic waves going back and forth between these two materials. So when some electromagnetic wave hits material 1, some of it is absorbed. The fraction that is absorbed, let's just call it A2 at the given frequency omega, and some of it will be reflected. And the reflected fraction, let's just call it R2 omega. And of course, this electromagnetic radiation will also hit the other material, and some of it will again be absorbed. Let's call the fraction that is absorbed by A1 omega, and that is emitted will be reflected is R2 of omega, R1 of omega. So in each absorption, of course, the materials are absorbing some energy. And when they are, okay, there is also their emission. Each one will be emitting some radiation also. Now so this reflection is basically can be imagined as some kind of an emission also. Now let's add the emission. Now the thing turns out to be this emission coefficient. I think it was the absorption coefficient. This is a universal constant. For all materials. So a black body is defined as AI is equal to 1. It basically absorbs everything that falls onto it. And since this ratio is a universal coefficient, independent of the material that you are using, so that coefficient is also independent of how you create the material. So basically, if you create some material which just absorbs everything that falls onto it, that is what we call a black body. Now the question is, how do you create such a material? Well, the easiest would be obtain a container. The surfaces shouldn't be perfect reflectors. They should be absorbing the light falling onto it. And of course, if you just imagine there is a hole over there, if you just imagine some light ray entering, it will just enter. And as it is bouncing back and forth, it will lose energy, and basically it will never come back. So here the black body is this part over here. It is the hole that is the black body, not the inside of the container, or not the radiation inside, not the walls. It's that hole. Well, of course, that hole, there will be also some radiation emitted from the hole. And that radiation emitted from the hole will be determined by the radiation inside our cavity. So if we study the radiation in thermal equilibrium inside the cavity, then we know what will be the radiation. Then we can calculate the radiation emitted by the hole, which is what we call the black body. And that emission, as I said before, is independent of how you create the black body. So this is just a model of the black body. Since the emission is a universal property of a black body, whichever method you use to create a black body, it will always be emitting the same spectrum. So that is what we will be doing. So first let's study what is the energy inside the black body. Well, the energy, you can just sum over all the modes, just like we did in the case of the sounds or vibrations. The average number of particles in that mode multiplied by the energy of the mode. Energy of the mode in this case is not approximately but exactly equal to h bar omega I. And just like before, we can convert this to an integral. Well, let me just pick up my expression. So it's just 4 pi 3 over c cubed dw omega squared omega squared h bar omega, and the average number of photons in this mode is given by the Bose-Einstein distribution. Well, of course, the allowed frequencies in this case is not limited, so the upper limit is just infinite. So let me just simplify it slightly. 4 pi. Well, okay, this is not 3 anymore, because you see, in the case of the sound waves, we said that they have 3 polarizations, but electromagnetic waves only have 2 polarizations, so we have a factor 2 only. So this is 8 pi over c cubed times v times h bar from 0 to infinity dw omega cube 1 over e to the power beta omega minus 1. This is my u. Well, I can evaluate this. Let me just make a change of variable. X is now beta omega, or omega is just kt. U is 8 pi over c cubed times v h bar from the omega is kt times x. So here I have kt to the 4 from 0 to infinity dx x cubed over e to the power x minus 1. Well, you see, that number is just, that integral is just a number. Well, you can just look up that number, whatever that is, or thanks to Mathematica, we can just ask Mathematica to evaluate it. X cubed divided by e to the power x minus 1. X from 0 to infinity. This is just pi to the 4 over 15. It's just a numerical value. So the internal energy of my system is 8 pi over c cubed v h bar pi to the 4 over 15 k to the 4 multiplied by t to the 4, which is also sometimes called a v sigma 4 sigma over c t to the 4. Energy density, which is u over v this is 4 over c sigma times T to the 4. Sigma being the Stefan-Boltzmann constant. And it is completely determined by the Planck's constant and the Boltzmann constant and somewhat speed of light. Now then this wasn't what we were, this is one thing we are interested in, what is the average energy of electromagnetic radiation in thermal equilibrium. But another question is, what about the black bodies? What is the power emitted through here? You see, we had already calculated it when we were looking at the kinematics of the ideal Bose gases. We had shown that the effusion coefficient, or so let's say it was the number of particles emitted per unit time per unit area. It was just 1/4 the average speed times the energy density. Now in this case the average speed is the same, c for everything, so the power emitted would be just u over v times c over 4. That's why I included this 4 over c over here. So this is just sigma times T to the 4. This is the famous Stefan-Boltzmann law for black body. It's basically 1/4 of the radiation is moving in the direction of the hole. That's why we have that 1 over 4. And the energy is moving at the speed c. Energy density is moving with the speed c, and only 1/4 of it is moving in this correct direction. That's why we have this c to the 4 factor. Now, what else we can look for? What about the pressure? Well, let me just call this power. This is the power. This is equal to energy emitted by the black body per unit area per time, per unit time. Well, I should repeat, this law is a property of the hole, of the black hole, or of the, sorry, not the black body, which is the hole. So since its properties are universal, independent of how you create the black body, this should be the same for all the black body. For example, you can apply this black body law to the sun, the radiation emitted by the sun. The surface of the sun is an almost perfect black body. There's no cavity there. There's no electromagnetic radiation in thermal equilibrium at the temperature of the surface there. But nevertheless, the surface, being a black body, should have the same properties as the hole in this setup. And hence its power should be, if it's a perfect black body at least, its power should be given by the Stefan-Boltzmann law. Now if you go back to the radiation inside, that radiation will have a pressure. Well, we can calculate that pressure. Remember, PV over KT was equal to the minus logarithm of Q. Well, I might be missing this minus sign, which is the sum of the logarithm of 1 or minus e to power minus beta epsilon. Since the partition function, the chemical potential is 1. In the exact expression here, we had a z minus 1. Z being e to power beta mu. Well, now I can calculate the pressure. PV is equal to KT times the sum of the logarithm of this number. Well, there's a minus sign also over here. Well, I can just repeat what I had done here. That's basically this expression. Of course, I don't have this h bar omega, that was the energy, and I don't have this term. Instead, I have the logarithm of 1 minus e to power minus beta epsilon, or epsilon is h bar omega. And then I have the minus kt term. Well, if I would like to compare this with the energy, well, in the energy expression I don't have the logarithm. I should have the 1 over e to power beta h bar omega minus 1. So I can just do an integration by part. So this will be equal to minus kt over 3, 4 pi 2 over c cubed v 0 to infinity dw, derivative of w cubed with respect to w of this logarithm. You see this 1 over 3 is when I take the derivative of w cubed, that brings a factor omega cubed. Now I can do an integration by part, but this time the boundary term will not contribute. So it will be minus kt over 3, or plus kt over 3, 4 pi 2 over c cubed, v from 0 to infinity dw, w cubed. Now the derivative of this one with respect to w would just bring beta h bar divided by e to power beta h bar omega minus 1. Well, you see this kt cancels this beta. So PV is equal to 1/3 4 pi times 2 over c cubed times v from 0 to infinity dw, w squared h bar w divided by e to power beta h bar w minus 1. But you see, this term over here is nothing but U, the total energy of my system. So all these factors with the integration, this is my sum over states. This is the energy of the mode with frequency omega, and this is 1 over, this number is the number of photons in that state. So PV is just U over 3. Or the pressure of this electromagnetic radiation is just the average energy density, the energy density divided by 3. So we also know the energy density. Well, what about the spectrum of this energy? This is the total energy. Which I can write as from 0 to infinity dw U of w, or let's say U over v. This is the energy density at frequency omega. And U of omega is just 8 pi over c cubed h bar omega cubed divided by e to power beta omega minus 1. Or let me rewrite it in a slightly different form. This will be 8 pi beta, sorry, here I have an h bar. H bar beta h bar omega squared divided by c cubed beta squared h bar divided by e to power beta h bar omega minus 1. Or let's say u of omega is equal to 8 pi over c cubed beta squared h bar times x squared over e to the power x minus 1, where x I had defined as beta h bar omega. Now if you would plot that function as a function of x, well, at small x, you see e to the power x, I can just make an expansion. So this is 1 plus x, 1 is cancelled by this one, so this is x squared over x, so it increases linearly at small x. At very large values of x, this is much larger than 1, so I can just ignore the 1. This is the dominant term, so it's just x squared e to the power minus x, so it decays exponentially. So this is how that function looks like. And it has essentially a maximum at some x0. This x0 is just a number. You see, if you look at this function that I'm plotting, there's no parameters there. x0 is just a numerical value. Whose value you can just look up. So it basically tells me that the maximum frequency is determined by beta h bar omega max is equal to x0, or omega max is equal to x0 over h bar times kt. The density of energy, the density is a function of the frequency, is maximum at some number that is proportional to the temperature of the system. So if you increase the temperature, you get higher and higher frequencies. Now, of course, this is not the, most of the time it's not really expressed in this form. What is usually done is, you see, we have the u over v. This is the w, u of w. But w is, in terms of lambda, c over lambda. So this is equal to, again from 0 to infinity, dw is c times d lambda over lambda squared u of c over lambda. This is as a function of the wavelength. Where now this u of lambda, this is the density as a function of the wavelength, the energy emitted per unit wavelength. This is c over lambda squared u of c over lambda. This is equal to c over lambda squared. Well, you see, we already know what u of u omega is. Here, x is now in terms of lambda is beta h bar c over lambda. Or lambda is equal to beta h bar c over x. So u of lambda is c beta h bar c squared. This from this lambda, 1 over lambda squared. No, 1 over lambda squared, there is a minus 2. squared 8 pi c cubed beta squared h bar x to the 4 divided by e to the power x minus 1. Now again, if you plot u of lambda as a function of lambda as a function of x, x to the 4, you will see more or less the same thing. At small x, it just goes as x cubed. This is at small x. At large x, again, due to this exponential, it will decay exponentially. So this will be the behavior as a function of x. And again, there is this point over here, which let's call this y0. Just keep in mind that y0 is not equal to x0. So there's a corresponding lambda max, which is beta h bar c over y0, which, by the way, is not equal to c over omega max. They're just shifted a bit because of this 4. You see, in the other one, it's just 2. This factor is 2. y0 is slightly larger than x0. And that's basically it about the black body radiation. We know the spectrum, we know the pressure, we know the power emitted. Any questions? Now, next week we will go into the details of Bose-Einstein condensation. But let me just summarize what the principle will be. Okay, so if we have a bosonic system, the total number of bosons, we know that it is given by sum over all the microstates, 1 over e to the power beta, epsilon minus mu minus 1. So let's see how these functions behave as a function of temperature. Also keep in mind that this equality basically fixes what mu should be as a function of the temperature and the volume, etc. And the number of particles. But let's just assume that if mu is fixed, so how does this function change as you lower the temperature as a function of epsilon? You see, as a function of epsilon, this function starts from some value, but it basically decays exponentially. Let's assume that mu is sufficiently small and sufficiently large and negative. So for all reasonable values of epsilon, that e to the power beta epsilon minus mu will be much larger than 1. So we can just ignore it, so it will be more or less exponential decay. Now what happens when I lower the temperature? Well, when I lower the temperature, beta just becomes larger. So it decays faster exponentially. So if, it decays. Now let me just slightly change this graph. You see, as a function of epsilon, when epsilon is equal to mu, it diverges. And then it gets smaller and smaller as epsilon gets larger and larger, and eventually for large enough epsilon, it starts to diverge exponentially, go to 0 exponentially. So this will be the behavior. Now, if I, at a given value of E, if I lower the temperature, well, this beta term gets larger and larger, so it will decay faster. So again, here it diverges. So it will be this one. You see, assuming this is T1, this is T2 less than T1. Mu fixed. So if you still interpret this as an occupation number of a given state, as you lower the temperature, the occupation number of the energy states gets smaller and smaller. Well, that will be kind of makes sense, especially for the excited states. As you lower the temperature, the number of particles in the excited state should get smaller and smaller. All of them try to go to the ground state. But then we have a problem though, if mu is fixed. You see, the problem is this sum over here is fixed by the number of particles I have. But if all the terms appearing in my sum is getting smaller and smaller, I cannot keep that number constant. So what should we do is some of those numbers should get larger and larger as I lower the temperature. But that means I just need to increase the value of mu. You see, as I lower the temperature, if I increase mu, let's say this is mu1, if mu2 is somewhere over here, the corresponding occupation number will start from somewhere above, and then it will decay exponentially. Okay, the exponential decay is faster because I'm at a lower temperature for large epsilon. For large epsilon, mu will not be relevant. So it will decay faster exponentially. But you see, in this region, the occupation number increases. Now that is also what we expect, because if we have this distribution of particles, if we distribute them in all our states, so as I lower the temperature, the number of particles in the excited states will get smaller, but the number of particles in the ground state or close to the ground states will get larger. So that's what we expect. So this argument basically tells us that, okay, we should show it more rigorously, but mu increases as the temperature decreases. So the chemical potential as a function of temperature should increase or decrease in magnitude. So I say this is our temperature. This is the mu. Let's say at some value of T it increases. Well, if it increases, this is the value of mu at some temperature. As I lower the temperature, mu should increase. So it's getting larger and larger values. So the question is, well, eventually it can hit 0. And in fact, as T goes to 0, T goes to 0, you see, if you look at this expression, as T goes to 0, that is beta goes to infinity. For epsilon larger than mu, this is 0. For epsilon is equal to mu and T goes to 0, I can have some finite number. It will be 0 over 0 uncertainty, etc. At T goes to 0, mu should be 0. So when does it reach the 0? At finite T or at small t? Or at 0 t. So it's possible that for certain systems it will reach 0 and then stay at 0. In some other systems it might just it might reach 0 only at T equal to 0. So this is what we call the Bose-Einstein condensation. You see, the number of particles in the ground state, let's say epsilon is equal to 0. will be given by 1 over e to power minus beta mu minus 1. So mu is equal to 0 basically means that this diverges. Well, that's not so problematic because keep in mind that we are dealing mainly within the thermodynamic limit. In the thermodynamic limit, when temperature goes to 0, all the particles are in the ground state, but the number of particles we have is already infinite. So this strictly being equal to 0 is valid only in the thermodynamic limit. And not in the finite system limit, this our mu, we will see that it will be proportional to 1 over n0. Or more precisely, z will be 1 minus 1 over n0. So mu is not strictly 0, but negligibly small. So this is what we call the Bose-Einstein condensation. And we will just, next week we will start on Wednesday we will study its thermodynamic properties. And then in our remaining time we will study the fermionic systems. Questions? So see you next week.